So there's the document. What you'll notice is first the equipment. Right. So we're going to be using 0.1 molar silver nitrate as our titrant. Well, actually, that's not the titrant, excuse me. What we're going to do is we're going to make up, let's go through the mechanics of it first. Let's go down here. Here we go. So what I've done is I've tried this experiment several semesters, and the ammonia with 3 molar concentration never seems to work, but the 1 molar works pretty well. So we're just going to limit it to 1 molar ammonia and 0.1 molar silver nitrate in these ratios. So we'll measure out exactly using a volumetric pipette, exactly 5 milliliters in 4 different Erlenmeyer flasks. And then into each one, we'll put successively 5 milliliters of 1 molar ammonia, 10 milliliters, 15, and 20 milliliters. And then we'll take that. Actually, we're not putting that in the Erlenmeyer flask, excuse me. We're putting this into a 100 milliliter volumetric flask, excuse me. So that means when we fill it to the mark, 100 milliliter mark, we've already added 10 milliliters, so the water we're adding is 90. In this one, we're adding 5 and 10, so we're only adding 85 water. That's what these mean. So the total of these 3 would be 100 milliliters. Okay. Then we're going to take each one of those and titrate it with potassium chloride of a known exact concentration. And we're going to add potassium chloride to the solution until we get a permanent presence of silver chloride. So how are you going to see the silver chloride? That's the trick. So once we've transferred that 100 milliliters into an Erlenmeyer flask, and we got a magnetic stir bar here keeping it mixed, and we've got our burette delivering known amounts of the 0.1 molar potassium chloride. Then we're shining a light through it. Now we're going to dim the lights in the room. Not so much you can't see what you're doing, but so that we can see the light beam travel through the solution. And when you're looking at it right angles, and if you can see that beam in there, that means that it is being bounced off the silver chloride particles. Okay. Before that, it'll go straight through and you won't see the beam. We're going to use the Tyndall effect to detect the exact point of equivalence. Okay. So once we have that, that's the volume that we put in this column for each one of these tests. Now the total volume, we need to know that because everything here is based upon concentration. So we need to know the total volume after the titration. So it'll be this volume plus 100 milliliters. Okay. Now the calculated KF takes some doing. So I need to talk to you about that a little bit. Let me look. Yeah, use the Tyndall effect. Okay. So I'll have a flashlight available. You don't have to bring one. Let's talk about this, deriving this equation in the blue box. Okay. All right. In the PowerPoint presentation, we had derived this equation. So the formation constant for this equilibrium is going to be the diamino silver 1 in the numerator and the ammonia and the silver in the denominator with the ammonia squared. That's the value we want, that Kf right there. Okay? But we need a way to get at it, right? Because it's not easy to determine something that you can't see, right? This is in solution. That's in solution. This is in solution. You can't see them. So that's why we have to titrate them. And the reaction is going to be a combination of the solubility product for silver chloride and the Kf, the expression for Kf. Okay, so we're going down here and let's derive that. Right. So the KSP, the Kf for that one is going to be the complex ion, right, divided by the ammonia squared and then silver. Okay. And we know the KSP for silver chloride. Right. KSP for silver chloride is 1.7 times 10 to the minus 10. So the KSP for silver chloride is equal to silver ions times chloride ions equals, what did I say, 1.7 times 10 to the minus 10. Okay. So we're going to solve this equation for silver and substitute it in here because we're going to be titrating with chloride ions. That needs to be part of the expression. Okay, so if we solve this for silver, then that's equal to KSP over chloride. Okay, so now we can substitute that in here. So we got the complex ion divided by ammonia squared, and then this expression, KSP divided by chloride ions. Right there. So that's as far as we've gotten so far. Remember, the denominator of the denominator is the numerator. So that's why this chloride moves up here. So we do that, and we put it up here. So this is a constant. We've got the value already. We have to calculate the concentration of ammonia, of this ion, and that chloride. And then we can calculate Kf. Okay, so that's the trick. How do you get at those values? All right. So I think I've got an example down here. Yeah. This chloride, well, we've actually got two chloride expressions. What we need to do is substitute, in order to use an ice table, we need to substitute for this one. That expression again. So we got a chloride here and a chloride there. Right? If we cancel the chlorides, we're back here. But we can use this as is based upon this equilibrium expression. I mean, if you break this out into an equation, these are the reactants, right? These are the reactants. Let me see. I'm going to have to put it over here. Break this out into an expression that we can build an ice table from. So this is going to be the product. This is going to be the reactants. No, this is going to be the product. This is going to be the reactants. So we're going to put 2 ammonias right here, and then silver, and then chloride in equilibrium with the complex ion and chloride. So we got chloride on both sides. So now we build an ice table from that. All right, so initial, change, equilibrium. All right. There's just one other trick. It's easier to work this ice table if we use absolute amounts. In this case, millimoles. And then we calculate the concentrations later. So initially, we have 0.5 millimoles. How did I get that? Well, let's see. I'm using probably the first one in the table. Yeah. So if we have 0.1 molar silver nitrate, 0.1 times 5 milliliters is 0.5 millimoles. So we'll go back down here. There's 0.5 millimoles of silver starting off with. Oh, I got them switched around. Okay, that's all right. 0.5 millimoles. How much ammonia did we have? We do the same calculation and we get 5 millimoles initially of ammonia. Okay. And we have 0.1 millimoles of chloride ions. Okay. How did I get that? Well, let's go back up. Oh, we need a volume. Okay. The titrant is potassium chloride. So if we say, okay, here we go. 5 milliliter aliquot of 0.1 molar silver nitrate was treated with 5 milliliters of 1 molar, diluted to 100. The solution was titrated with, okay, so the amount of titrant chloride ions is 1 milliliter times 0.1. Which is 0.1 millimoles. That's initially. We've titrated it to its endpoint. That's where we start. And at this point, we're saying, okay, there's none of this. Right? And there's none of that on that side because we haven't formed this one yet. So at the equivalence point, we use up all the silver over here. Right, so this is going to be, the change is we're going to get rid of that, right? And how much of this is it going to take? Well, it takes twice as much ammonia as silver. So we're going to subtract twice of that, right, of the ammonia. And we're going to use up all the chloride too. All the chloride is gone. Okay. Now, where did it go? Well, we got 1 silver. So that means we have this one, 0.5 millimoles here. So how much chloride do you have? Well, it disappeared from here and it showed up over here. Okay. Now we can do, what's the equilibrium? Well, now we only have 4 millimoles of ammonia left. We have no silver on this side. We have no chloride on that side, but we do have chloride on this side. And we have the complex ion. So we have 0.5 millimole here. And we have 0.1 millimole of chloride. Okay. So now we have the absolute amounts of each one. What we need is the concentration. So with this many millimoles, what's the total volume? Well, we started off with 100 milliliters, and then we added 1 milliliter of titrant, 1 milliliter of potassium chloride. So the total is 101 milliliters. So remember, millimoles divided by milliliters is molarity. So that's what we're doing here. We're taking the millimoles of ammonia divided by 101. That gives us that molarity. This molarity for the silver, for the complex ion, this molarity for the chloride. And there's your, again, your solubility product for silver chloride. Then now all we have to do is plug it into that equation. Now we modified the equation so that we could get this together. But the solution is this equation right here. We've determined, excuse me, not that equation, the KSP with the chloride in it. So we get rid of that, put the KSP back. KSP times square of ammonia divided into chloride and complex ion. And that's what we've done here. We put those concentration values in and calculate the value. Did it calculate the value? Oh, here it is. KF 1.84 times 10 to the 7th. That would be the experimental determination. And we compare that to the accepted value, which is somewhere around here. Maybe it's up in the discussion. Yeah, I think it's in the discussion. So let's see what the accepted value for the formation constant is. Up here somewhere. Huh. I have to be sure and bring it so we can compare. Okay, maybe I put it in a later version. This may be an earlier version on my memory stick. Yeah, I don't see it. In fact, there's supposed to be some more to this than there is. Okay, so it's a lot of trouble to get there, but this is the logic. And by doing it this way, we can calculate this in one fell swoop, as long as we get these values in line. The one thing that happens sometimes is that each of those titrations doesn't work well. So this first one, if we get a good value there and we have time, then we'll go to the next one and see if we can do that one. Otherwise, we'll just leave it at 1, depending on how it goes. Okay, any questions? Well, in that case, I'm going to stop the share. Okay. And we're done early.